In the mid-1950s, the Cold War was a silent, high-stakes battle of technology. The primary threat was not an invasion, but a wave of high-altitude Soviet bombers carrying nuclear weapons. To stop them, America needed more than just a fighter. It needed a shield. It needed the ultimate interceptor. From this requirement came the Convair F-106 Delta Dart, which took its first flight in 1956. This restored historical footage chronicles the development of what was for decades the backbone of America's air defense. The F-106, affectionately known as the Six, was an aircraft built around a computer. It was one of the very first integrated weapon systems. Its brain was the formidable Hughes MA-1 fire control system, a complex piece of engineering that could, in theory, fly the entire mission. The F-106 was designed to be linked directly to the SAGE ground control network, which could vector the aircraft to its target, manage the attack, and even fire its weapons, with the pilot acting as a system monitor. Its revolutionary design philosophy was most obvious in its armament. Early F-106s were pure interceptors, built for a single, devastating pass. They carried no gun. Their lethality was stored in an internal bay, which would snap open to fire Falcon missiles and the notorious AIR-2 Genie. The Genie was an unguided rocket tipped with a 1.5 kiloton nuclear warhead, designed to destroy an entire bomber formation with a single shot. The Six was also a thoroughbred of performance. It was a marvel of the area rule design, giving it that classic, pinched Coke bottle fuselage, which allowed it to slip past Mach 2 with ease. In 1959, an F-106A set the world's absolute speed record at an astonishing 1,526 miles per hour. But perhaps the most famous story that speaks to the F-106's unique character is that of the Cornfield Bomber. In 1970, a pilot entered a flat spin and was forced to eject, but the act of ejecting, combined with the change in balance, popped the aircraft out of the spin. The F-106, with its engines idling, gently descended and bellied itself into a snowy Montana cornfield, sustaining so little damage it was repaired and returned to service. For nearly 30 years, the F-106 Delta Dart stood guard over North America. It was the last dedicated interceptor in the U.S. Air Force inventory, a true Cold War sentinel.
The F-106 is designed to be a fully capable, highly effective, all-weather interceptor for use by the United States Air Force Air Defense Command units. Deliveries to these units will start in 1959. The tactical versions of the Convair F-106A single place and the F-106B dual place are supersonic Mach 2 aircraft powered by the Pratt & Whitney J-75 P-17 engine. Both carry their armament internally, with basic armament for each consisting of 4 Falcon missiles and 1 MB-1 nuclear rocket. Test activities for the year 1958 involved detailed testing of all elements of the weapons system, from laboratory testing of components to an extensive flight program. The F-106A and B Accelerated Development Program involved 42 aircraft, of which 17 were assigned to the contractor portion of the test program. This film report will present the significant highlights of the 1958 program. For the purpose of this report, the program will be divided into 3 sections. The first, or flight test section, will concern those activities covered in the actual flight program. The second, or support testing phase, will involve those component activities investigated through laboratory-controlled examinations. And the final armament section will report on the development program designed to demonstrate F-106 armament delivery capability. At the Air Force Flight Test Center, in-flight examinations included evaluations of the F-106 external wing tanks, F-106A spin testing, J-75 engine evaluations, and the initial flight and preliminary flight test evaluations of the F-106B aircraft. Early in the year, aircraft 56-451 was assigned to the spin program. This program was conducted to determine the stall and spin characteristics for F-106A aircraft. Aircraft 451 received all special spin equipment installations at Convair San Diego Experimental Facility before being returned to Edwards Flight Test Center for the flight program. Recovery strakes installed on each side of the aircraft could be extended during a spin to assist in spin recovery. A spin recovery chute was installed in a special container mounted at the base of the vertical fin. Used as a secondary safety precaution against spin conditions, this device was activated by ballistically firing a pilot chute into the airstream, pulling the recovery chute behind it. Special pilot safety equipment included a single-action ejection seat and a modified G-suit to protect the pilot against longitudinal G-loads in the event of high spin rates. All equipment was thoroughly tested in flight examinations to ensure proper performance before beginning the spin investigations. A total of 31 spins were made, beginning with preliminary spins in April of 1958. Initially, recovery was made before a fully developed spin was reached. Later spins were allowed to progress until the full spin was accomplished. During these developed spins, a condition was encountered where the airplane would gyrate after stalling. This condition came to be known as a post-stall gyration. Detailed examinations of this condition determined its cause, the warnings preceding it, and the proper recovery technique necessary. Analysis of the data obtained in the spin program demonstrated F-106A compliance with the applicable Air Force specifications. Following completion of the spin program, aircraft 56-451 was stripped of all special spin equipment, provisions were added to carry external fuel, and a program was conducted to clear all F-106A and B aircraft to carry and use the external drop tanks. At the completion of tank installations on the aircraft, ground shake tests were made, clearing the aircraft for flight flutter testing at the Air Force Flight Test Center. These tests were satisfactorily completed with full tank loads at altitudes of 5,000 and 15,000 feet. Speeds were at Mach 0.75, 0.85, and 0.95. During jettison testing, 9 tanks were expended, 7 single-tank jettisons, and 1 dual jettison. Altitudes were at 15,000 and 35,000 feet. The drops were accomplished at 2 different speeds, Mach 0.4 and 0.95. At the conclusion of the program, external fuel usage testing was completed on aircraft 452 up to a speed of Mach 0.95, with altitudes ranging to 40,000 feet in climb, dive, and level flight conditions. As a result of this program, sufficient data was obtained to clear all F-106A and B aircraft to carry and use external drop tanks. During the 1958 test program, several changes were made in the F-106 propulsion system to improve propulsion and aircraft performance. Thinning of the external inlet duct cowlings resulted in a satisfactory drag improvement. The slotted ramp replaced the earlier perforated ramp. This change increased pressure recovery due to improved bleeding of boundary air and resulted in a 3% increase in thrust. A flight program to determine optimum ramp scheduling for the new slotted ramp established ramp operational standards for all production aircraft. 5 tail cone configurations were evaluated in a program consisting of 22 flight missions. The original cone, shortened by 4.6 inches, resulted in an effective combination of drag thrust improvement. Improvements in ejector design led to the acceptance of the convergent divergent ejector, with a resulting thrust increase of 8% at design speed over the basic engine configuration. The Pratt & Whitney J75 P-17 engine was accepted for all F-106 aircraft over the earlier P-1 and P-9 versions. This engine included all basic improvements made in the earlier models. Rotating of the first stage inlet guide vanes and thinning of the second stage inlet guide vanes increased the flow area and resulted in relieving of low-energy stalls. First stage turbine inlet guide vanes were changed to a new alloy with heat characteristics that allowed higher operating temperatures than alloys used in earlier models of the J75 engines. The results of the propulsion program have confirmed the compatibility of the F-106 airframe and the J75 P-17 engine. These improvements have raised installed engine thrust and temperature limits to design specification requirements. F-106 aircraft, in which all of the new modifications have been incorporated, have now flown at the design speed of Mach 2. The first F-106B aircraft, 57-2507, moved off the production line at Convair, San Diego during the early part of 1958. The aircraft was then delivered by truck to the Air Force Flight Test Center, and after thorough ground checkout evaluations, made a successful first flight on April 10th. The F-106B is designed to be a fully capable two-place interceptor aircraft with a complete F-106 armament system. It will serve as a tactical aircraft and, in addition, be used to familiarize pilots with the F-106A weapons system. Similar in appearance to the F-106A, the F-106B has a longer and slightly raised canopy. Dimensions are equal to that of the A. Wingspan, 38 feet, 1 inch. Overall length, 70 feet, 8 inches. Height to the tip of the vertical stabilizer, 20 feet, 3 inches. The approximate takeoff gross weight with full internal fuel load is 34,751 pounds. As a result of the similarity between the A and the B, the 1958 B flight test program was primarily devoted to examination of the significant differences between the two aircraft. Preliminary results have demonstrated that the F-106B maintains the same excellent handling characteristics of the F-106A. Climb and acceleration performance is essentially the same, with general performance in other areas comparable to the F-106A. Thorough testing of the complex electronic cooling and air conditions systems of an F-106 aircraft would be impractical using normal flight test methods. Necessary instrumentation and time would be very costly to the development program. For these reasons, an electronic cooling test stand laboratory was built at the contractor's San Diego testing area. The test stand chamber will hold an entire F-106 fuselage and is capable of recreating both transient and steady state temperature and altitude conditions for the entire flight range of an F-106 aircraft. Temperature can be varied from minus 60 degrees to 220 degrees Fahrenheit. The test stand method produces the data and development information necessary in proving the F-106 electronic cooling system adequate to the great demands made on it in actual flight operation. Changes in the F-106 cooling system, when proved necessary by test stand investigation, are incorporated into production aircraft following retest approval. A brief flight program confirms test stand results. The data available from this testing would be impossible to obtain without the test stand facility. The resulting savings in cost and time have proved invaluable in the F-106 development program. The skin of the 9 fuel tanks dispersed throughout the wings and fuselage of the F-106 are designed to withstand thermal stress as well as stress due to internal tank pressure and flight loads. The contractor established the Point Loma Structures test site in conjunction with the Air Force to test the effectiveness of the machine-sculptured, Scotch-weld-bonded tank skins. The jig work, electrical, fuel, and hydraulic systems here are adequate to subject fuel tank test specimens to a full range of simulated flight conditions. The tests conducted were on 3 tanks: the forward wing tank, the wing transfer tank, and the fuselage tank. Each tank was placed in its own special jig to most accurately apply flight loading conditions. All internal and external flight load conditions encountered in the full range of operation of an F-106 were mechanically produced through whiffletree and hydraulic actuator arrangements. Both static and extensive cycling loads tests were conducted through varying temperature conditions ranging from sub-zero through ambient to hot. Reduction of the data recorded from thermocouples, strain gauges, and other instrumentation determined that the machine-sculptured integral Scotch weld wing tanks met design requirements. For the purpose of developing a high-efficiency F-106 radome, a special research and design group was formed within the electronics section of Convair San Diego as early as September 1955. Primary mission of the group was the development of a high-efficiency radome for the F-106. The basic concern was to design a radome which would allow efficient passage of the radiated energy search beam, and to ensure that the radar waves would complete passage through the radome with as little distortion as possible. The ideal radome would be electrically transparent, causing no radiation distortion. Since this is impossible, the distortions of the best possible radome must be measured and compensated for. To back up the design predictions based on this theory, the radome laboratory tested many radome experimental shapes with their complete test facilities. Bore sight range, direct physical measurement, high temperature dielectrometer, free space interferometer, and other complex equipment were employed. From this background of research and testing, the Convair Radome Design Group has developed a radome shape and manufacturing technique which meets the demanding performance requirements of the F-106 fire control system. The technique has resulted in 2 major conclusions. 1, it has reduced the insertion phase difference, or IPD variation, from 10 electrical degrees to 1. And 2, it makes practical a method of reproduction with high physical standard from part to part. In addition, engineers can now predict electrical performance in terms of known radar properties and can maintain electrical variations within extremely narrow error tolerances. Matched to the gimbal of the MA-1, the radar antenna is individually bore-sighted to ensure accurate installation, and final checks are made before the delivery of the aircraft to the Air Force. With these newly developed design, development testing, and manufacturing methods, a very high degree of accuracy has been obtained in this vital component of the fire control system. With today's interceptor aircraft pressing farther and farther into the range of supersonic speeds, the need and urgency for developing a pilot ejection system that will function at subsonic, transonic, and supersonic speeds at minimum and maximum altitudes is vital. In view of this, the Industry Crew Escape Systems Committee was formed to coordinate a developmental approach to safe ejection from supersonic aircraft. First considerations included both an upward ejection system and a downward ejection system. The Air Force assigned Convair the responsibility of developing the needed upward ejection system for Century Series aircraft. In Convair's program, two types of seats were originally considered: the A, or skip flow generator type, and the B, or bobsled type. After initial evaluations, Convair, with the approval of the ICESC committee, concentrated its development efforts on the second, or B, seat design. The pilot is ejected on his back at a 90-degree launch attitude, a launch position especially desirable because G-loads tolerances for humans are greatest at this angle. Preliminary wind tunnel and slingshot testing of a 1/10th scale model led to a full-scale wind blast program at the Air Force Flight Test Center. These runs were used to indicate the wind blast forces on the seat and pilot. In all, there were 5 runs conducted at speeds of 627 to 858 knots. Both low and high altitude flight gear was examined for wind blast results. In all post-run examinations of this test series, the pilot and his personal equipment was found to be in near pre-run condition. The first full-scale aerodynamic testing of the B seat was accomplished on the ARDC supersonic missile and rocket track at Hurricane Mesa, Utah. 3 objectives were accomplished in this test series. 1, the full-scale seat-simulated ejection performance as planned. 2, the validity of the slingshot tests were verified by the flight attitude of the seat. And 3, the test confirmed the results of the previous wind blast tests on the pilot and personal equipment. It was established that the seat configuration had good yaw and pitch stability, but did have excessive roll. At this point, telescopic booms were added to control the roll. Following slingshot evaluations, further testing at Hurricane Mesa using the new booms resulted in near-perfect seat flight, with no pitch, no yaw, and with only a negligible roll. During 1958, testing of the complete B-seat ejection system was conducted on the sled run track at the Air Force Flight Test Center. Speed for this series ranged from 132 to 750 knots. Results of the program to date have demonstrated that the B seat, as developed, will provide a reliable upward escape system for today's supersonic aircraft pilots. To date, this is the only type seat that has been successfully ejected from a sled-simulated aircraft cockpit at supersonic airspeed and remained aerodynamically stable and maintained accelerations within human tolerance. The sled tests showed that the configurations were stable over a speed range extending from 132 to 750 knots. It is felt that the operating principles of the B seat may be extended to much higher speed while maintaining good low-level, low-speed performance. In 1959, the B seat will go into hardware production for installation in tactical F-106 Interceptor aircraft. Initial F-106 armament phases and test programs are conducted at the Missile Development Center at Holloman Air Force Base, New Mexico. The activities here have fallen into two general categories: those involving Convair armament subsystems testing, and those involving a joint contractor Air Force effort to harmonize the overall system. The Convair aircraft, numbers 458 and 460, were engaged in MB-1 ejection and ballistic studies and Falcon missile launching evaluations. The MB-1 ejection and ballistics program comprised a series of tests to demonstrate the compatibility of the unguided nuclear warhead rocket and the ejection system of the F-106. Prior to any live firings from an aircraft, inert rockets were ejected under various flight conditions. These tests determined rocket separation characteristics, but indicated that at a high Q condition, the rockets had high nose-up characteristics. This was corrected by a baffle and a 2-inch shorter stroke for the aft gun. Live motored rocket tests were made next to obtain clearance of the F-106A flight envelope. To date, MB-1s have been ejected on this program at speeds from Mach 0.9 to Mach 2 and over an altitude range of 10,000 to over 50,000 feet. The MB-1 ejection launcher proved efficient and highly reliable through repeated firings. The AD program, or Armament and Aircraft Weapons Control System Development Program, is a joint effort among the Air Force, Convair, Hughes, and Douglas. Among the primary objectives of this program was the flight operation of the highly advanced fire control system, the MA-1, designed and built by Hughes Aircraft. This MA-1 system is composed of many subsystems, each in itself a complex system: search and tracking radar, digital computer, communications system, navigational aid components, landing system aids, automatic flight control systems to be activated when cleared, and the armament auxiliary equipment. The MB-1 manual firing phase was started in December of 1958. 3 successful firings were made at an altitude of 20,000 feet and at a speed of Mach 1.25 against manned targets. The AD program provided the necessary changes required to give proven capability to tactical type F-106s in manual mode MB-1 firings. The accomplishments of the F-106 all-weather supersonic interceptor in its armament and in all flight testing to date has lived up to every design prediction.
We continue with a short film that explores the origins and history of the other Century fighters. After the hectic development period of World War II and the ensuing rush into jet engine development, a successive series of fighter aircraft emerged that made their mark in aviation history. These planes epitomized the shape of the supersonic jet fighter. They were the Century fighters. After the close of the Second World War, there was a period of great expansion in jet engine development. The release of German design data spurred on the second generation of jet fighter aircraft, in particular the concepts in swept-wing designs. Previously, jet aircraft designs had maintained the straight-wing concepts of their propeller-driven forebears. These had also brought with them the speed and maneuverability limitations associated with wings designed for slower existing speeds. World affairs at the time were also turning frosty between the Soviet and American governments. The worsening dialogue between the nations saw the world marching towards the Cold War period. World fear was raised another notch in 1949 when the Soviets displayed reverse-engineered B-29 Fortresses as their Tu-4 long-range bombers. And having previously tested their own nuclear weapons, American defense analysts were forced to rethink their Air Force requirements. The American fighter inventory at the time had the North American-built F-86 Sabre. This was a very technically advanced fighter for its day. The 35-degree swept wing, exceptional view, and hydraulic control surfaces made this a favorite of many fighter pilots. To counter the threat of the Soviet long-range bombers, the F-86s were designed as interception fighters and armed with a cluster of 6 half-inch machine guns in the nose of the plane and a rack of unguided rockets mounted under the fuselage. A favorite at air shows was the sonic boom produced by the planes to impress the crowds. These fighters were publicly seen to be the plane of the future and as the cutting edge of American Air Force. The middle of 1950 saw a new battleground in the skies above Korea. Originally, the Sabres were to be used as bomber escorts for the B-29s, destroying the North Korean infrastructure. On the 1st of November, though, Russian MiG-15s stunned the American pilots with their performance. These aircraft were much further advanced than the American concepts of Russian jet development. The B-29s, even with their defensive armament, were no match for the outstanding MiGs. The Sabres were then sent to defend the bombers, and so began the fighter versus fighter combat that would become the MiG and Sabre discussion that continues to this day. One of the primary advantages of the MiG over the Sabre was its 50,000-foot service ceiling, 10,000 feet above that of the F-86s. There was nothing that the Sabre pilots could do unless the MiGs decided to come down and do battle. However, one of the most serious weaknesses of the MiG-15 was its tendency to go into uncontrollable spins, especially in the hands of inexperienced pilots. Many Sabre victories in Korea were scored without the F-86 pilots ever having to fire their guns. They merely forced their MiG opponents into spins from which their pilots could not recover. By the end of the conflict, the facts that had proven most decisive were that, as the U.S. Air Force had no clear air superiority at that time, it was U.S. pilots and crews, who were all highly trained and experienced airmen, that made the difference. Whereas, with the exception of some Russian World War II veterans, the MiG pilots were often sent into combat with only limited training and flying experience. The F-86 models were phased out of the Air Force inventory within a year after the Korean War. However, 5 new fighters were then in research and development phases. They were popularly called the Century series due to their 100-plus designations. 3 of these aircraft, the F-100, the F-101, and the YF-102, were descended from existing fighter designs. The remaining 2, the F-103 and the F-104, were entirely new concepts. The Air Force considered the F-100 Sabre, later called the Super Sabre, to be an improvement of the latest F-86 design and ordered it for immediate production. The F-100 was more than an updated F-86, however. The new aircraft incorporated a 45-degree angle swept wing, a larger fuselage, new armament, and a new engine, the J57P7 Pratt & Whitney turbojet, complete with afterburner. North American Aviation completed much of the design on its own. The Air Force ordered production models of the aircraft in 1952, skipping the usual prototype testing phase. The first flight of the YF-100A took place on the 25th of May 1953 with no major deficiencies noted. That first flight was a stunning success. Piloted by North American's chief test pilot, George Welch, the YF-100A actually broke the sound barrier on its maiden voyage, an incredible achievement for a brand new design and a clear signal that the supersonic era had truly begun. By mid-year, however, three problems became apparent: low-speed handling characteristics, poor visibility over the nose during takeoff and landing, and inadequate static and dynamic stability. Two of the problems were quickly rectified, but the issue of low-speed handling, particularly on landings and takeoff, was to plague the Super Sabre throughout its life. The F-100 went on to become a specialist ground attack fighter bomber and was used in extensive deployment during the Vietnam conflict and the Rolling Thunder program. The F-101 Voodoo from McDonnell was a swept-wing twin-engine jet fighter. Like the F-100, the F-101 also used the J-57 engines, 4 20mm T-160 cannon, and built-in air refueling equipment. New aircraft planned to replace the F-84 made its first flight in the fall of 1954 and entered service in 1957. In addition to its role as bomber escort, the aircraft had strategic striking and air-to-air combat capabilities. The Air Force also adapted the aircraft for reconnaissance missions. The Convair F-106 Delta Dagger single-seat all-weather interceptor was the first delta-wing combat aircraft in the world to enter operational service. It was also the world's first all-weather interceptor capable of supersonic performance in level flight. It was the first fighter to have an all-missile armament provided as standard from the very start of the initial design stage. The YF-103 was an even more high-performance interceptor being developed by Republic Aviation at the same time as the F-102. However, in 1954, funds were denied for an extended development program, and in 1957, the program was canceled altogether. Development of the Lockheed F-104 Starfighter, an advanced day fighter scheduled to replace the F-100, began in 1952, but didn't make significant progress until mid-1954. This aircraft, called a minimum concept weapon, was meant to perform air superiority missions at lower expense than its more complex contemporaries. The F-104 had a thin, straight wing attached to a long, slender fuselage and was able to reach a top speed of Mach 2. The design, championed by the legendary Skunk Works engineer Kelly Johnson, was a direct response to combat experience in Korea. Pilots had requested a simpler, lightweight fighter that prioritized sheer speed and climb rate above all else. The resulting wings were so remarkably thin and sharp that protective guards had to be fitted on the leading edges while on the ground to prevent injuries to the ground crews. Although the aircraft made its first flight in 1956, it didn't enter operational service until 2 years later. Later designs followed, each embodying a different philosophy. The outstanding F-105 Thunderchief was built for sheer power and payload. The F-106 Delta Dart, a further development of Convair's Delta Dagger, represented the peak of automated interception, and the radical F-107 from North American pushed the boundaries of aerodynamic design. All of the aircraft in the series had their initial problems. Most were dealt with in further development, but some became part and parcel of the job description of jet fighter pilot. With the speeds now being achieved by the planes, the concept of landing became somewhat of an exercise in controlled chaos. One F-100 fighter pilot with over 2,000 hours experience in the type described landing his Hun as nothing more than a controlled crash. The landing difficulties which were experienced by the pilots also extended to having a very long roll session if the deceleration chute failed on the tarmac. Of the most worrisome, though, was still the lack of low-speed maneuverability characteristics of the plane on landing. Here, the pilot has seen he's undershooting his landing point and attempts to pull his plane up. In opening the throttle too quickly, he's induced compressor stall and the plane has sunk below a controllable speed. The resulting overcorrections have only compounded the problem, and the final result was catastrophic. At times, this problem became common enough for it to be given the term saber dance. Though this became the bane of many of the Century fighters, it was not, in particular, a design flaw as such. It was only that the airframes were designed with one purpose, and that was to go fast. The design requirements for supersonic speeds are not at all forgiving at slow speeds. As a result, no landing was ever to be taken for granted in a Century fighter. Many of the aircraft were further developed after their initial acceptance. The F-104 from Lockheed was initially designed as an interception and air superiority fighter. It was occasionally described as a manned missile, and almost supported the fact as the tiny wings were bolted onto the outside skin of the aircraft. The Starfighter was also one of the very unforgiving styles of Century fighter. The German Luftwaffe lost over 200 planes in accidents. Though little blame was apportioned to the plane itself. For a significant period, the F-104 itself was widely regarded as the hottest plane in the air. In spite of its initial testing problems with in-flight pitch-up, it went on to set and hold most records in speed, height, and climb at one time. Even when the F-4 Phantom II broke the Starfighter's records, the F-104 reset them outside the F-4's abilities. Further developments of the airframe were later required to meet customer demands. The in-flight refueling concept, taken for granted today, had to be invented for the Century series. Significant retrofitting, though, was required for the F-104 to be able to successfully deliver the unguided Genie nuclear rocket. With the plane's fuselage fully occupied with its engine, some concerns of how to provide separation before firing led to an elaborate trapeze concept for launching the weapon. Testing showed the 104 easily coped with all the new requirements, though it still failed to generate any large U.S. orders. The Genie missile was powered by a Thiokol Tu-389 rocket motor and was unguided, relying on its 1.5 kiloton nuclear warhead to ensure a kill. Launch weight was 822 pounds, and maximum velocity was Mach 3.3. Snap-out fins gave the missile stability during flight. Range was about 8 miles, and flight time to target was about 12 seconds. One of the most significant marks of Lockheed's F-104 was that, although it didn't achieve major domestic sales in the U.S., its production did run for over 30 years for various NATO air forces and stayed in service even longer. On June 11, 1954, the U.S. Air Force authorized the contract for North America's next fighter project, the F-100B fighter bomber. On July 8th, the Air Force notified North American that the designation for the project had been officially changed to F-107A. Since this aircraft was so vastly different from the original F-100A, it deserved a completely new fighter designation. This new aircraft, briefly known as the Ultra Sabre, was a complete departure, aimed squarely at a high-speed tactical strike role. In comparison with the original F-100, with a top speed of around Mach 1.25, the F-107 was 50% longer and could achieve closer to Mach 2 as an interceptor. Also, moving the engine intake from the nose to the top of the fuselage just behind the cockpit allowed for conformal storage inside the fuselage of various nuclear weapons. The first F-107A took off on its maiden flight on September 10, 1956, at Edwards Air Force Base, with North American's test pilot Bob Baker at the controls. It went supersonic on its first flight, although there was some minor damage upon landing when the drag chute malfunctioned and the aircraft overran the end of the concrete runway and ended up in a ditch. The aircraft was quickly repaired and flew again 3 days later. The F-107A found itself in direct competition with the Republic F-105 Thunder Chief for production orders. In March 1957, the U.S. Air Force decided to go with the F-105, and the F-107 was relegated to aerodynamic testing duties. The North American F-107 is widely regarded today as one of the best planes never to go into service. The F-105 Thunder Chief was the first supersonic tactical fighter bomber that was developed from scratch for this role. All others before it were adaptations of aircraft that had originally been developed as pure fighters. The Thunder Chief has the distinction of being the largest single-seat, single-engine fighter ever built. Although designed for the nuclear strike role, the Thunder Chief gained distinction for the role it played in the Vietnam War in delivering conventional ordnance on targets in the north. The first YF-105A rolled out of the factory in the autumn of 1955. It was shipped to Edwards Air Force Base for initial trials over the Mojave Desert. The first flight of the YF-105A took place on October 22, 1955. It easily exceeded the speed of sound on its first flight, although, as expected, the transonic drag was quite high. It was the largest and heaviest single-seat fighter ever built up to that time. At the controls was Republic's test pilot, Russell "Rusty" Roth. Remarkably, this supersonic feat was achieved with a temporary non-afterburning Pratt & Whitney J57 engine, as the intended J75 was still in development. On January 30, 1957, the YF-105B, equipped with the new Pratt & Whitney J75 turbojet engine, took off on its first flight. The maximum speed reached during tests was Mach 2.15, which was remarkable considering the weight of the plane. Interestingly, the Convair F-106A was to use the same Pratt & Whitney J75 engine as the Thunder Chief, though later developments saw it fitted with an even more powerful version of the J75. In mid-1957, the F-106A was given the popular name Delta Dart and went on to be regarded by many as being the finest all-weather interceptor ever built. It served on active duty with the U.S. Air Force for almost 28 years, much longer than most of its contemporaries. This was the true, ultimate interceptor of the Air Defense Command. Despite the Thunder Chief's large size and weight, in May of 1963, the F-105B was selected to replace the F-100C Super Sabres of the Thunderbird's flight demonstration team. The Thunderbird's team flew a few demonstrations with their F-105Bs, but a serious accident occurred in May. This fatal crash, caused by a catastrophic structural failure during a high-G maneuver, immediately grounded the team's thuds. The modifications directed as a result of this accident prevented the use of the F-105Bs in any more public air shows. Because of its heavy schedule, the Thunderbird's team was hastily re-equipped with 8 F-100D Super Sabres. Here, the Thunderbirds are putting their Huns through one of the display sequences they've become so well known for. The F-100Ds remained with the Thunderbirds until 1969, when the team was re-equipped with F-4E Phantoms.
Stopping the loop now, ease it off, let it float. All right, back in with the pull. Now let's ease it off and play the deck. Move off, now.
Although many of the Century series of fighter aircraft had inherent flaws, all of them played extraordinary roles in the development of today's aeronautical technology. They have truly made their marks as the Century fighters.